Hi there, my name is Andrew, and for this video tutorial I'll be giving a brief introduction into planar Newton-Euler dynamics of rigid bodies. For rigid bodies, we are concerned with both translational and rotational motion. However, Newton's second law of motion only provides enough equations to solve for translational motion, so we're going to need more equations for the rotational motion. So for the rotational motion, we look at Euler's second law of motion, which states that the rate of change of angular momentum, h, about an axis is equal to the sum of the external moments m about that point. In most cases, we choose that point to be the center of mass, denoted by g. Now, in a planar setting, we can define angular momentum as the product of mass moment of inertia, which we've been introduced to already in first year mechanics, as well as angular acceleration. So our final equation for rotational motion can be the sum of moments about center of mass g is equal to the mass moment of inertia times by the angular acceleration. For these equations, the bar over the acceleration and the moment of inertia just indicates that they are with respect to the center of mass. These two equations are the basis for Newton-Euler dynamics and will get us through most rigid body equations. So, let's apply our knowledge to an exam question. So in this question, it says the space shuttle's altitude control engines exert two forces as shown, with Ff equals to 8 kilonewtons and Fr equals to 2 kilonewtons. The shuttle has a mass of 54 tons and a moment of inertia of 4.5 times 10 to the power of 6 kilograms meter squared, about its center of mass g. Ignoring gravity, find the acceleration of the center of mass and the angular acceleration of the shuttle. Okay, so we're going to apply our equations for translational and rotational motion now. But before we start this question, I've always found it very helpful to just identify what the question's asking and the information that we've been given. Okay, so we want the angular acceleration of the shuttle, which is denoted by alpha, and we want the acceleration of the center of mass, which is a bar, or you can write ag. We've been given the forces Ff and Fr. As you can see, I've denoted the direction they're in. We've been given the mass of 54 tons. I've converted that to kilograms to keep things in SI units. And we've also been given I bar or Ig, the moment of inertia about the center of mass. Alright, so let's start the question. Now the first step in doing any rigid body analysis is going to be draw a free body diagram. This will simply simplify the situation. So as you can see, I've created my free body diagram of the question. So the free body diagram simply allows us to identify the important components and simplify the overall question. So I have my center of mass g, and I have my forces at F and R, as you can see, and I've included the dimensions of them with respect to the center of mass. Now, we would normally also have the weight force created by the mass of the shuttle. However, this question has asked us to ignore gravity, hence I've not included it in the free body diagram. Okay, so for the angular acceleration of the shuttle, we know that the angular acceleration is directly related to the sum of moments about g, as well as the mass moment of inertia. Okay, so that's our equation for rotational motion. Now for the following analysis, we need to give a sign convention, so we're going to make counterclockwise the positive. Let's start with determining the sum of moments about the center of mass g. So they're going to be moments created by these forces over here. So what we're going to do is simply simplify these forces into the x and y components and determine the moments they create about g. Okay, so you should all be very familiar with doing this from first year mechanics. So for example, the x component of F is going to be Ff cos 5. Okay, that's acting 2 meters perpendicularly to the center of mass, and it's creating a moment in the clockwise direction, hence it's negative. Okay, Ff is simply going to be the y component. Ff sin 5, sorry, is going to be the y component of F, and Fr cos 6 is the x component of R, and Fr sin 6 is the y component. So we should all be comfortable doing that. That's going to equal to negative 1919.28 Newton meters. The negative symbol simply indicates that it's going in the opposite direction to our sign convention. Hence, it's going to be counterclockwise. Sorry, clockwise. So for the angular acceleration of the shuttle, we're simply going to make angular acceleration the subject. So rearranging the rotational motion equation, angular acceleration is going to be equal to the sum of moment divided by the mass moment of inertia. Sum of moments we've just determined is going to be negative 1919.28, and the mass moment of inertia was already given in the question, 4.5 times 10 to the power of 6 kilograms per meter squared. Okay, so equating that, it's going to give us our final answer. So therefore, the angular acceleration of the shuttle is 4.265 times 10 to the power of 4 rads per second squared. Because of the negative symbol, we know it's in the opposite direction to our sign convention, hence it's going to be clockwise. The next part of the question asks us for the acceleration of the center of mass, sum of forces, as well as the mass of the object. Okay, so this is Newton's second law. Very simple stuff. So first, we're going to determine the resultant force, or the sum of forces. Okay, so that's simply going to be using our equilibrium equations in the x and y direction. So let's sum the forces in the x direction. We're going to create our sign convention going to the right as positive, so therefore x component of f is going to be ff cos 5, and x component of r is going to be fr cos 6, and because it's moving to the left, it's going to be negative. Summing those together will give us 5,980.51 newtons. In the y direction, we're going to have the y components of f and r, and we're going to have the mass, the weight force. However, we're going to ignore the weight force because the question asks us to ignore gravity. Okay, so this value here will go towards 0. Summing these two values is going to give us negative 906.3 newtons. Once again, the negative symbol means it's just in the opposite direction to our sign convention. Hence, the y component of the resultant force is acting down. To find the resultant force, we need to sum our x and y components, and we're just going to do that very simply using Pythagoras' theorem, and that's going to give us 6,048.79 newtons. So, back to what the question was originally asking, the acceleration of the center of mass. We're simply going to make that acceleration the subject. So therefore, acceleration of the center of mass denoted by a bar, so the bar indicates that it's with respect to the center of mass, it's going to be equal to the resultant force F over the mass of the object M. That's going to be equal to 6,048.79 over 54 tons, which we've already converted to 54,000 kilograms. And that's going to give us 0.112 meters per second. The second part of the question is very similar to the first, except now they've simply changed conditions. So let's read the question. Now suppose Ff is now equal to 4 kilonewtons, and we desire the angular acceleration to be 0. What must Fr be, and what is the resulting acceleration of the center of mass? Okay, so now instead of giving us Ff and Fr, they've told us Ff, and they're asking us for Fr if this angular acceleration is going to be 0. So, once again, we're going to just identify what the question's asking for and what we've been given. So the question wants us to find Fr, given that the angular acceleration is 0, as we can see, and we also want to find the acceleration of the center of mass. Free body diagram. Let's get into it. Okay. Once again, the first step is going to be to draw exchange. Once again, we are ignoring the weight force as the question told us to ignore gravity. So, for Fr, if Ff is equal to 4 kilonewtons and we desire the angular acceleration to be equal to 0, that means from our rotational motion equation, which is the sum of moments is equal to the mass moment of inertia times by angular acceleration, that's actually all going to be equal to 0 because the angular acceleration is 0. So therefore, the sum of moments about the center of mass is equal to 0. And we know from our previous analysis in part A, we already have an equation for the sum of moments, as we can see. Okay, so the entire sum of moments here is going to be equal to 0. We know Ff, we don't know Fr, and so hence from this equation we're going to be able to determine Fr. So simply rearranging the equation, bringing the Fr components and factorizing them to one side and the Ff components to the other side. So subbing in Ff, that's going to give us 1,694.34, and then making Fr the subject, That's going to give us Fi equals to 2036.16 newtons. For the acceleration of center of mass, for the second part of the equation, once again, we know that the acceleration of center of mass is directly related to sum of forces and the mass of the object. So that's Newton's second law. And we know from the previous question that we're going to have to find the resultant force, which is simply the sum of the x and y components, sum of the squares of the x and y components. So once again, let's determine the forces in the x and y directions using our equilibrium equations. So, forces in the x direction, that's going to be x component of ff and the x component of fr, as we can see. And that's going to give us 1691.25 newtons. For the y direction, once again our sign convention is going to be pointing down, hence we have negative ff sine 5, negative fr sine 6. And you can see we've ignored the weight force, but the net weight force would normally be positive mg over here. That's going to give us negative 589.67 newtons. Summing the x and y components to determine fr, and subbing and rearranging this equation to give us the acceleration of the center of mass. That's going to be acceleration of the center of mass is equal to sum of Fr, or the resultant force, over the mass of the object. Okay, and Fr is determined to be 1791.10 newtons. Okay, so that's simply using this equation over here for the resultant force, and we know the mass is 54,000 kilograms. So therefore, the acceleration of center of mass is going to be 0.033 meters per second squared. Okay, so that's the end of the tutorial there. Okay, so it's a simple application of Newton-Euler dynamics. Okay, so you can see we only have two equations for equations in the rotational and translational motion. Those equations can be modified, say, if we're not, if we don't want to find the moment about g, and we want to find out about a certain other reference point O, and then of course we'll have to use other concepts of physics such as parallel axis theorem, things like that. Okay, but we'll cover that in a later video. Thank you, I hope that was helpful. Goodbye.